Welcome students. In this lecture, we'll discuss the mass transport. Okay. So what is Fick's law for binary diffusion? Okay. So let's begin. So you already know Fick's law. So what is the Fick's law? So Fick's law is given for mass transfer, right? So generally the Fick's law is written as like JA minus DAB and delta C by delta X. Okay, this is a concentration. Okay, let's first understand the terms. Okay, so this is flux. Okay, this is molar flux. That means it will be mole per meter square per second. Okay, of A. Okay, mole of A, because we are calculating the molar flux of A. Okay, what is this? Concentration difference of A. Let's say we have 2 points here. Let's say this is CA1, CA2. Okay, so let's say CA1 is higher than CA2. So mass transfer will take place from in this direction, right? From CA1 to CA2. Okay, from this point to this point. Okay, so C1 is nothing but molar concentration. So mole per liter or mole per meter cube, you can say. Okay, delta X is definitely in meter because distance. So this is nothing but concentration gradient. Okay, and what is DAB? This is called mass diffusivity. Okay, this is mass. The units are meter square per second. So okay, why do we write DAB? Okay, what do you mean by A and B? So Fick's law is generally for binary diffusion. Okay, binary diffusion. Binary means we have two species, like let's say A and B molecules. They are diffusing in each other or one in other. Okay, so we have two species A and B. So let's say A is diffusing into B. Okay, let's say I have a B gas here, only B gas is here. Let's say here at this point I have a concentration of CA1, and at this point I have CA2. Let's say CA1 is greater than CA2. So definitely these molecules, species A molecules, try to diffuse through this to this point, right? Because there is a concentration gradient. Okay. So in this process, if the species A wants to move from this point to this point, then it has to go through this. Okay. So the diffusivity will change, right? If there is nothing in here, there is no molecule B here, then diffusivity will be something different. If it is pure air, right? So because the molecules will will provide some resistance to the molecules of A, okay, while moving. Okay, so that is the diffusivity. We write, if A is moving through B, we write the diffusivity as A in B, DAB. DAB means A is diffusivity of A in B. A is moving through the B. If I write DBA, that means B is moving through A. The diffusivity of B in A. Okay. Generally for binary diffusion, DAB and DBA are equal. Okay. So this is the Fick's law. Okay. This is of the same form as the heat transfer and the momentum transfer. Okay. The thing is you can express this Fick's law in mass concentration as well. This is in molar. This is molar flux, right? I can also say it is mass flux. So if you want to calculate the flux in units of mass, not in molar. So this was in molar flux. Let's write. So if you want to calculate the mass flux, only you have to change the concentration term. So AV. Instead of writing molar concentration, I will write mass concentration. That is, earlier it was mole per meter cube, right? This one. So I just want to write in the form of kg per meter cube. As you know, the density is nothing but kg per meter cube. So I will write this delta X. So this is nothing but mass concentration, kg per meter cube, and everything remains same. Then J will become mass flux. The units of JA will be kg meter square. Also, you can write in terms of mass fraction or molar fraction. How? You can write the same equation in the form of mass fraction or molar fraction. Let's see. You can rewrite this equation as, let's say density is constant, and so definitely, let's say this at this point it was rho 1 or rho 2. Okay, so the mass transfer will happen from this to this, right? So it is delta rho. Okay, generally density is constant, right? So you can write instead of this, so you can write, let's say here the mass fraction is omega 1, here the mass fraction is omega 2. So you can write, if the rho density is constant, so rho W1 will give you the density at this point, and rho W2, this will give the density at this point. Okay, so you can take out the common, so we will have omega. Okay, omega by delta X. So this is in mass fraction. This is mass fraction. Okay, same equation. So we can also write this into molar fraction. So how to write that? So J, everything remains same. Just take out the concentration. Let's say this is average concentration. Similarly, this was average density. Okay, so this is average. So you have molar fraction 1 minus 2 divided by delta X. Or you write delta, don't confuse with X, Y. This is generally we use X for molar fraction. Okay, so this is nothing but delta X by delta Y. Okay, so you can write it like this, all are same. And also you can say if the flux is happening in X direction, so you can write X, JAX. So molar flux of A in the direction X. Okay, or you can say JAY, molar flux of A in the direction Y, or you can write Z, molar flux of A in the direction of Z. Similarly here, you can write Y, it is a mass flux of A in the direction Y, or mass flux of A in the direction of X. That's some of the notations. Okay, you already know this stuff. So in this chapter, we have again same example, same kind of analogy like before. So if you see here, we have, so let's say we have a slab, silica. Okay, silica is generally porous, so gas can diffuse through it. So here we have air, and let's say here it is helium. Okay, of some concentration. Let's say we have here, we put helium here. There is no helium here, no helium, only air. So definitely there is a helium here of higher concentration. There is 0 concentration, right? So there will be mass transfer will happen. So the helium will transfer from this point to this point. Okay, because there is a concentration gradient of helium. Okay, let's say I denote the species helium as A and the silica as B. Okay, right? So because the helium have to diffuse through the silica, so we can write the diffusivity as something like DAB. Okay, so this is the scenario. So we have drawn it again in this form. So at T less than 0, there is no concentration gradient, because here also air, here also air. I haven't put helium here yet. Okay, at T equal to 0, I just put the helium here. Okay, on this side. Okay, with some concentration WA or WA naught, we can say, at T equal to 0. Okay, so this omega is nothing but, this is mass fraction. Okay, so as the time progresses, what will happen? The helium try to diffuse through it, and at this point, the helium concentration will decrease, right? You can see here, this is nothing as plot. This is the distance and how the helium concentration is. Okay, this is the helium concentration. So helium concentration is highest at this point, right? At y equal to 0. At y equal to 0, helium is the highest concentration, right? And as you move along at the side, helium concentration will decrease. Okay, right? So it is given in the mass fraction. So mass fraction will decrease as you move along this height. And at very large time, when a steady state is achieved, then what will happen? You'll get this linear line. Okay, so this is the initial concentration of the helium, and it has completely diffused through the silica. Okay, so you'll get a linear profile. From this experiment, you can approximate like this. This relation holds. So what is WAY? So this is the mass rate. So it will be in kg per, let's second. What is A? This is the area. This is the area. Let's say the slab area is like this. So since diffusion is happening in this direction, right? So you have to take this area or this area. Okay, so area is meter square. And what is rho? This is mass concentration, kg per meter cube. This is diffusivity, meter square per second. This is the initial concentration of the helium at this point, and the final concentration, we don't have any helium on this side, so it is 0, right? So we have written 0 here. Okay, and the distance between the transfer, so this is y, right? So we have this. So so you can write like this, or you can rewrite this in this form. Okay, so this was mass flow rate divided by area is nothing but mass flux. Okay, so J, small j in this book denotes this is mass flux, kg per meter square per second, and this is mass concentration. This is diffusivity of the helium, that is denoted by A, in silica, that is denoted by B, and this is your concentration gradient. You have mass concentration, so the omega A by dy in that direction. Okay, so this is also again Fick's law, already you know that. So we're generally talking of binary mixture. Okay, so binary mixture means we have only two species, A and B. There can be more than the two species, A, B, C. Then you have to find the multi-component diffusivity. Okay, the A in C, B. So there's formulas to calculate the multi-component diffusivity. So in this course, we'll generally discuss the binary diffusion. So we have only take the two species, A and B. Okay, so let's discuss some of the terms. mass average velocity. What is the mass average velocity? So what is the velocity of the whole mass? We have two speeds, right? A and B. So what? How will define the average? So we have to take the weighted average, because these mass fractions are given ma, let's say mb, or in this book the notation is omega a, omega b. So you can write, let's say the velocity of the species A is v a y in this y direction, right? So where in this example the mass transfer is happening in y direction, yeah, okay, and the velocity of B in y direction is, let's say, vby. Okay, so I want the average velocity of these two gases, the mixture. So I will define it like this. So mass fraction omega A into VAY plus mass fraction of B into velocity of B in the y direction. Okay. Similarly, if the mass transfer is happening in the x direction, you can write omega A, velocity of the A in x direction, velocity of omega B, velocity of B in x direction. So this is the average velocity in x direction, right? And similarly, you can do the in the z direction. Okay. So this is called mass average velocity. Now, this is the general diffusion definition of the mass flux. So you take rho omega A and VAY minus VY. So this is what? This is mass flux in the y direction. This is the mass concentration. This is the mass fraction of A, because you are calculating the mass flux of A. This is the velocity of A. And what is Vy? This is the average mass average velocity in the y direction. Okay, so this is also the another definition to calculate the mass flux. Okay, and if you are talking about binary diffusion, generally total, if you do the mass conservation, so JAY plus JBY equal to 0. We're generally talking about molecular mass transfer. So this is true. This is generally 0 for binary diffusion. Okay. Also, you can write the same. So this was done for the single direction y. Okay, you can do it for all the three directions. So you just write it the vector, right? On on paper you have to write this like this, and again this row is a vector in the three directions, just in the bold. DAB is also same, you can say isotropic, it is same in all directions. Then the gradient vector in all the three directions, right? So you can write this in vector form. Again, you can write for this vector form. This was for mass flux of A. You can write the mass flux of B in the same form. Okay, and let's see some of the dimensionless groups. So this is Prandtl number, mu Cp by K. This is your mu by rho, and alpha is K by rho Cp. So this is the ratio of momentum diffusivity by thermal diffusivity. This is Schmidt number. This is rho by nu by DAB. That is nothing but mu by rho by DAB. This is called Schmidt number. This is the ratio of momentum diffusivity by mass diffusivity. This is analogous. Okay. And we have Lewis number. That is alpha by DAB. That is thermal diffusivity by mass diffusivity. Okay. Let's try to discuss the how diffusivity varies with temperature and pressure. Here's a plot between the reduced temperature and the reduced self-diffusivity. Okay, so just see the trend. Okay, so here we have temperature axis and there's a diffusivity axis. So what happens if I increase the temperature? Okay, we have two here. So for gas and for liquid. See, dotted lines are for liquid. Okay, so first we'll discuss the gas. Okay, for gas, as you increase the temperature, what is happening? So this dark lines is, so this all dark lines have same trend, it increases. So as the temperatures increase for gases, the diffusivity will increase. Okay, we don't write this the DAB because this is not binary diffusivity. This is the self diffusivity. In let's say A is diffusing inside A only. Okay, this is self diffusivity. So diffusivity will increase according to this graph. Okay, for gas. Now let's consider pressure. What happens if you increase the pressure? So you have to check here. So we have different lines. This one at different pressure. If you say low pressure limit, this is at reduced pressure of 2. This is at reduced pressure of 5. So this is reduced pressure of 10. So pressure is increasing with this in this direction. Okay. So let's fix the temperature. So let's say fix this temperature. So what is here you can observe is that so this line is of higher pressure, reduced pressure of 10, so highest pressure. So what is happening if you increase the pressure? So this pressure is increasing in this direction, right? Or you can say in this direction. So as you increase the pressure, you can see at constant pressure, the diffusivity is decreasing. Okay, the is decreasing. Okay, for gases. So if you increase the pressure, there will be more collisions, more resistance to the molecules movement. So there will be lesser diffusivity. Okay. Now let's consider liquids. So if you consider liquids, so you can see the dotted line. This is for liquids. I'm talking about self diffusivity. So if you increase the temperature, same trend, so it is increasing, right? So diffusivity will increase if you increase the temperature for liquids also. What about pressure? So increase or decrease, there is no line here. So there is no effect on the diffusivity with increase or decrease in pressure. So diffusivity is independent of pressure for liquids. Okay. So lastly, we'll discuss the transport by convection. The Fick's law is generally given for molecular transport. Okay, that is the diffusion by molecular mechanism only. So that is molecular transport. Okay, but we have to also consider the convective. Okay, only in heat transfer we have 3 modes of transport. That is molecular transport, that is conductance, that is, and then convective mode, that is your that is also there, and the thirdly radiation. Okay, and in mass and momentum transfer we have only 2 modes of transport, that is your molecular transport and the convective transport. Okay, so in this mass transport case we call it diffusion, the molecular transport. Okay, so let's study the convection part. Okay, before understanding convection, we have to we can write the convection or the transport in 2 units. One is mass units or and molar units. Okay, one in terms of kg and one in terms of mole, or you can say kg mole. Okay, so let's study few of the notations. So I will compare it here. So let's say here mass units. On this side we have molar. So what is the mass concentration? This density. What is the molar concentration? This C. Okay, let's I write rho A. Let's say it's for species A. Okay, so what is this? Kg per meter cube. This is mole per liter or meter cube. Then how will you define the mass fraction omega A? Right. Let's say we have 2 species B. Then this written. So rho A plus rho B and rho A. Right? So you can write rho as total concentration. Right. Similarly, here mole fraction is defined as Ca by CA plus CB. You can write this CA plus A as capital C. Okay. Let's define mass average and molar average velocity. Mass average velocity. And here molar average velocity. So this is nothing but the weighted average. So if you are calculating the mass average velocity, then you have to write like this. V velocity of species A and mass fraction of species A, velocity of species B, and mass fraction of the species. See, this is a vector. Okay, earlier I have shown this equation in the particular direction, x or y, right? So if you write x, then you have to write x here as well. Okay, but I have written this in vector form, so you have to consider all the three components, right? And what about the molar average velocity? We write it like this, v star. Okay, all in vector form. So this is same molar concentration, velocity of A, and the molar concentration of A plus velocity of B, and the mole fraction, mole fraction of the B, right? This is star. So this is very important, and you have to, I think this is mass average velocity, right? So you have to, okay, let me check. Generally it is defined as rho A VA, right? Mass concentration of A and this, and then you divide it by, so generally the definition is like this, mass average velocity. I skip this part. So if we are talking about two species, so mass concentration of A, velocity of A, plus mass concentration of B, velocity of B, all direction, and total concentration, right? Rho A, it's rho B. But this is nothing but rho, right? So you can take out the common, so you can write rho A by rho VA plus rho B by rho VB. So this is nothing but the mass fraction, right? So you can write omega A VA vector. I mean, you can write like omega A VA plus omega B VB. Okay. Similarly here it can be derived in the same way. So the definition is actually like this: CA VA plus CB VB divided by CA plus CB. So CA plus CB is nothing but total concentration C. Then take out common. This is nothing but mole fraction of A. This will give you mole fraction of B. So you will get this. Okay. We have also defined the molar average velocity. Okay, so let's see this term. What is this one? So VA and V. This is, and what is this? VA star. So V was mass average velocity, V star was all vector, V star was molar average velocity. Okay, so this is, if you can see here, so this is nothing but relative velocities, right? Relative motion. Okay, so you have to see the relative motion. So if you see the relative motion with respect to the mass average velocity, and this is the relative motion with respect to molar average velocity. Okay, so this is the relative velocity of species A with respect to the molar average velocity, and this is the velocity of A species with respect to the mass average velocity. Okay, similarly you can write for B component, that is VB minus V. This is relative velocity of species B with in the mass unit terms, that is mass average velocity, This is the relative velocity of species B in with respect to the molar average velocity in molar units. Okay. This. Okay. So now you can write for molecular flux. That is divisible. So molecular flux is written as small j, right? So JA vector definition was CA B A minus V A star. You can write like this. This is molar units, or you can, this is molar units, or you can write in mass units like rho A. We're calculating the flux, mass flux or molar flux of species A minus VA. Okay. Okay. Also, you know, this is equal to the Fick's law. It is given by, so C DAB. We're talking about binary diffusion, and delta X delta Y. Let's say distance. This is the molar fraction, and if this is mass, you have to take omega. That is your mass fraction. Delta Y, and you have total concentration and DAB. Definitely minus is there. Okay. So if you can remember this. Okay, now let's talk about the convective flux. So convective flux in both units, mass and molar terms. So if you see this is, let's say I want to calculate the convective flux of species A. Okay. So this is right. The V is the velocity of the fluid. Okay. So if you check the units, so kg per meter cube into meter per second. So if you can see here, it is, so it is mass flux, right? Similarly, if you write CAV, then it will have mole per meter cube into meter per second, that is mole per meter square second, that is your molar flux, right? So this conductive flux is defined like this. In mass units, this is density, mass concentration into velocity. In molar units, it is molar concentration velocity. Okay. Same thing is written here. Okay. So V means it is mass average velocity. V star means molar average velocity. Okay. So if you are calculating the convective flux in terms of mass units, and you have to take multiply with the mass average velocity. If you are want convective flux in terms of the molar units, then you have to multiply with the molar average velocity. Okay. Then, so total mass transport will be a sum of molecular transport plus the convective transport. Okay. So let's say combined mass flow in mass unit. So we denote it small, let's say small a, I mean small n, and the species A. So it will be molecular transport given by Fick's law and the convective transport that is given by rho A. This V is your mass average velocity. And if you want to calculate the molar flux, I mean total molar flux in the in terms of molar units, then you have to write capital N. Let's say for species A, we have JA plus CA V star. Okay. That is how you write. So this is a total combined mass and molar fluxes. Okay. In next class, we'll discuss the shell mass balances. Okay, or transport equations. Okay. Thank you.